This video on visual odometry and optic flow and their application in a planetary exploration is based on a chapter from the book Planetary Rovers, Robotic Exploration of the Solar System by Alex Ellery. Now, before we can start with the video, we need to define what visual odometry actually is. Visual odometry is a vision-based motion estimation technique that estimates ego motion of a stereo camera through its environment in all 6 degrees of freedom, meaning that given a sequence of either stereoscopic or monocular images, we want to determine the pitch, roll, and yaw of the camera as well as any translational movement. Now, why do we even need this? Estimating the relative position of our rover is necessary to know how far it still has to go to complete its command. If we tell our rover that it should drive 2 meters, it needs to know when the goal is reached, otherwise it will overshoot and potentially drive into a rock and get damaged. Now, the cheapest way to add odometry to a rover is to use wheeled odometry. In other words, you just slap an encoder on each wheel. This, however, is extremely susceptible to slipping. On the rover Opportunity, the wheeled odometry had a discrepancy of 10% over a distance of 19 meters. So it is not usable for precise positioning information. Another option on Earth is GPS. It's a very convenient solution if the infrastructure already exists. However, on Mars there is no infrastructure. There is no constellation of GPS satellites that can be used, and building up such a constellation would be prohibitively expensive. Therefore, the logical compromise is visual odometry. We will start this video by taking a look at different types of visual odometry. After that, we will take a closer look at feature-based visual odometry, the more traditional way to do it, that is also used on Mars rovers. Then we will look at optic flow, a more modern technique that might find use on future missions. Lastly, we will compare the two types of visual odometry that we took a closer look on before. Now let's talk about the different types of visual odometry. Visual odometry can either be monocular or stereo. It can either be feature-based or direct. Both of those options, obviously, are mutually exclusive. Then there also is another option. It can be visual inertial odometry. In that case, the visual odometry is aided by an inertial measurement unit, an IMU. This is the most common type when used in drones. Rovers, on the other hand, tend to have stereoscopic feature-based odometry. As for them, accuracy is more important than speed. Now let's take a look at feature-based visual odometry. First of all, we actually have to acquire an image. It sounds stupidly simple, but it actually is not, especially when doing a stereoscopic visual odometry. In that case, it's extremely important for both of the pictures to be taken at the same time, as any difference, any variation in timing of the images will result in a wrong position of the feature in 3D space. After that, we need to find features. In order to find features, we use an algorithm like Harris corner detector. Such an algorithm then is applied until a certain amount of features has been reached. As a rule of thumb, this number usually lies in the few hundreds, but may be higher or lower depending on the application. Furthermore, it is important that not all features are in one area, as if this area then moves out of frame in the next picture, we would lose tracking. Now that we have found the features, we need to calculate their exact position in 3D space. In order to do that, we can perform a simple cross-checking algorithm for stereoscopic images, while for monocular images we need to perform bundle adjustment. In the left image, you can see all the features that have been found, marked by crosses. On the right side, you can see the black rectangles in which the cross-correlation search searches for the features corresponding to the ones on the left image. The blue crosses mark features that have been successfully cross-correlated, while the red ones were not found. The 3D position of the cross-correlated features then can be determined. Now that we have found the 3D position of each feature in each frame, we need to cross-correlate these features between the time frames in order to calculate motion. In the upper image, you can see all the features that have been found and whose coordinates have already been calculated. The blue crosses mark features that have also been found in the prior image, with the lines linking those corresponding points. The red crosses mark features that have not been found in the old image. The camera motion in all of this is the inverse of the average motion of the features, plus some error. Stereoscopic cameras also have limitations in their depth perception. The relatively short baseline distance means that at a certain distance, the accuracy of distance measurements suffers. It is the same problem that we humans have with our short baseline distance between our eyes. Visual odometry in general also has another limitation. If a large object in a frame moves, the algorithm cannot always perform the proper filtering. This happened to Opportunity on solar day 235 when it saw its own shadow during driving and miscalculated its motion. The footage you are seeing right now was taken during Perseverance's first auto-nav drive, meaning it is autonomously navigating during this shot. I wanted to show you this video to illustrate the kind of raw material these algorithms have to work with. In the next shot, you can see what the software makes out of it. In this case, however, no visual odometry was used. Due to its high demand for computational resources, visual odometry is only used sparsely for rover navigation. Opportunity, for example, only used visual odometry for 11% of its first 5.95 kilometer traverse. Visual odometry is only used when wheel slipping is expected, for example on inclines or declines. On the Mir missions, one step required 2 to 3 minutes of computational time, just to give you an idea. Now let's look at a technique that's quite a bit newer, optical flow. It's also sometimes called direct or featureless visual odometry, as it omits the step of extracting features and rather calculates motion vectors on a per-pixel basis. This, however, does not mean that it doesn't need features in the frame. In a flat desert, for example, it would struggle the same way traditional visual odometry would. Optical flow generally is a gradient-based approach that calculates motion on a pixel or even sub-pixel level. Large motions in between frames, however, can break the algorithm. And by large motions, I mean such in the neighborhood of around 10 pixels. So really not that large. All of the algorithms work on the assumption that movement locally is similar. That is, that two neighboring pixels move in the same direction. This assumption can break when it comes to edges. Optical flow also can be broken through the aperture problem. This is a theoretical problem that also occurs in the real world. We look at a slot of an image, so just one part of it, and there's a line moving across the slot. The question is, in which direction does the line move? Down, or to the right, or diagonally, somewhere in between? This uncertainty also can break optical flow-based algorithms. Now let's look at three different algorithms for optical flow. First, the Horn and Chunk algorithm is a global approach that iterates over every pixel. Therefore, it is less susceptible to the aperture problem. However, it also is pretty slow. The Lucas and Kennedy algorithm, on the other hand, is a local approach that always looks at patches of pixels, for example 5 by 5, similar to a kernel. Due to its local nature, it is more susceptible to the aperture problem. While the first two were differential approaches, the Fleet and Jepson algorithm is phase-based and uses orientation-sensitive filters. It is the most accurate of the three, but also requires the most computational power. Nowadays, a lot of deep learning-based algorithms are also being created. All of the approaches I just mentioned generate an optic flow field. Within this field, there are two important points: the focus of expansion and the focus of contraction. The focus of expansion is the point from which the flow vectors seem to originate, and the focus of contraction, conversely, is the point where they seem to disappear. The relative position of these points determines the translational and rotational movement of the camera. To better illustrate the usefulness of optic flow fields, this image shows the pattern that would be calculated when a camera rolls left. This illustration depicts a fly instead of a camera. Nevertheless, that does not change the usefulness of this example. In fact, a lot of insects take an approach to vision that is similar to optic flow. In the next image, it's not the camera that's moving, instead it's the horses on the beach. This underlines the usefulness of optic flow for other issues such as semantic segmentation. It can also be used as an advanced motion sensor. Now last but not least, let's compare the two approaches. Visual odometry requires the rover to stop, while optical flow can be calculated during motion. With visual odometry, however, the distance between frames can be larger. While optical flow only allows distances on a pixel or subpixel level, visual odometry allows for up to 75 centimeters or 18 degrees rotation between frames. This is necessary to have enough overlapping features to not lose tracking. Even though the computing power required to calculate one frame of optical flow is much lower, the higher number of frames means that visual odometry actually is less computationally expensive. This advantage, however, can be offset if the optical flow algorithm is implemented in specialized hardware. One example of such specialized hardware is the optical sensor of a modern computer mouse. It essentially is an image sensor, like in a camera, just with a much lower resolution, but therefore higher refresh rate. Most computer mice have a polling rate of 1000 Hz, while high-end gaming mice sometimes have an even higher one. It remains to be seen how much use optical flow will see in future planetary exploration. At this point, I want to correct a mistake I made during the talk I gave accompanying this video. I had claimed that the Mars helicopter Ingenuity was using optical flow to calculate its position. It turns out that statement was wrong. I based that claim on a third-party source, since at that time I hadn't found the paper from NASA on that topic. The claim also seemed reasonable, as most terrestrial drones use optical flow for that purpose. After a few additional hours of research, however, I did find a paper from NASA, which states that a feature-based algorithm actually is what's being used on the vehicle. As stated in the beginning, this video was mainly based on the book Planetary Rovers, Robotic Exploration of the Solar System. Some additional information was taken from the article Visual Odometry on the Mars Exploration Rovers by NASA that was published in the IEEE Robotics and Automation magazine in June of 2006. The sources for the visual material are directly attached to the corresponding clips. Thanks for watching.